Yeah. Okay, so yeah, so just now the guy mentioning about the Chinese style of study, right? Sit there and listen and then do exercise. Okay. So he mentioned about one thing, he said that the lecture note is the cumulative work between teachers and students. So this is what the thing I'm trying to do. Okay. So maybe you will listen while you listen, go through the lecture, right? You will hear something flip-flop, but I think you have to get used to it. Okay. Because in reality, right, it is flip-flop. Okay. In reality, it is flip-flop. Okay. There's nothing that is always true. Okay. So between this flip-flop, how you decide what is truth, what's reality is really important for you. Okay. If you can't differentiate these, then it's too bad. Okay. Okay. So I go back and look through my notes again. Okay. Last time we proved this theorem here. Prove that this is the formula for directional derivative. Okay. I found out there's some place that we can't really split the sum up. Okay. So first, it is okay that we use this definition of directional derivative. Okay. Hope everyone sees this. Okay. It is okay we use this. Okay. We add extra term. Okay. Sure. But how do we split this limit here? Remember that the limit can be split only when the limit exists. Okay, we don't even know whether the limit exists or not. So I think we can't just split it. Okay, but what to do? What to do here? Actually, there's an easy way to do it. Actually, very easy, but maybe I also overlooked at that time. Okay, just by using the definition of differentiability. Okay, what's the definition of differentiability? Anyone recall? When does a function differentiable? Yeah, so let me get rid of unnecessary stuff. Let's write down the definition when f is okay. So what's the definition of f being differentiable? F a plus del x, comma b plus del y, and then equal ab plus fx ab del x plus symmetric unit fyb is it fyab del y, and then epsilon 1 del x, epsilon 2 del y. Okay, is that all? When epsilon, when which one? Okay, sorry. When, so let me, when del x del y go to 0, then epsilon go to 0. Okay. So this is differentiability at where? At the point AB. Okay. Does anyone have objection to this definition or not? You can check it. You can check it on your lecture notes. Okay. You don't need just look at this. Check your lecture notes. Confirm. Is it right? Is that right? Okay. This is right. Okay. So we have common ground here. Okay. So f, if f is differentiable at AB, what does it mean? It means that from nearby point, you can approximate using FAB. Nearby AB, you can just approximate using FAB. Okay, using what? Using the two partial derivative. Okay, with some delta x and delta y, and then add up some changes in your domain. Okay. So these changes should go really, really small. Remember, when we zoom into FAB, it should be just a linear plane. Trying to say. Yeah. Is that okay? Okay. So this question says that it is differentiable function of x and y. What does it mean? It is differentiable at every point. Okay, it is differentiable at every point. Okay. In particular, at every point, you can express as the linearization. Okay. So you can express as a linearization here. Okay, you can express as a linearization here. Okay. So yeah, so how? So how do you use this property here? Can you use the property here or not? Hmm? Yeah, so just substitute your equality to the first line here, right? Okay, because you can estimate all the nearby point using just fxy, okay, and the rest. So how to use this definition here? Well, let's see how do we use this. Okay, so let's see how we use this. By the way, this is very important. All the proof I present in the class is very important. It will come out in exam. Okay, so now is your chance to understand it. Now is your chance to bother me. Okay, so please bother me. Okay, so you use the definition of differentiability. Okay, so like Ziqian say here, right? So if it is differentiable, we can rewrite the first term here. How do we rewrite it? Why? How we rewrite this term? By using the equality. Sure. Above. Sure. Rewriting it at So become what? Xy. Yeah, sure. Xy plus f partial derivative x. Okay. And then at where? At sure. And then what's delta x in this case? Delta yeah, what's the delta x in this case? Yeah, HA. Good. And then yeah, this. I mean second you still have a second derivative. Yeah. Fy, xy. What's the delta y in this case? HB, good. Okay, plus. Anything else you want to plus? Epsilon 1. Yeah, sure. Let's do that first. Epsilon 1. HA. Okay, HA. Plus epsilon 2. HB. Minus fx over. Okay. But when we bring this delta x, delta h to 0, this epsilon and epsilon 2 also go to 0, right? Okay. So this means what do you left with? What do you left with? Okay, maybe let's us simplify simplify this expression first, right? Okay, let us simplify it first. So we see that fxy minus fxy, okay? And then we see all the h disappear, correct? Cancel out. Okay, what we left with is fx xy times a plus f of y of xy times b plus epsilon 1a plus epsilon 2b. Okay? Okay. So let's see how far is this from our statement that what we want to prove. How far is it from our statement? Huh? Just the epsilon term. Okay? Does the epsilon term disappear? Yes, right. Okay, because it is differentiable at AB. So when you take h go to 0, epsilon 1, epsilon 2 also go to 0. Okay, so by differentiability, this is exactly fx xy times a plus fy xy times b. Okay, because the previous two term doesn't have term that depend on h the change. Okay, yeah. So I provide you two proof here, so you can understand both of them. Try to understand both. Okay, any question on the proof or not? Okay, so in the exam, later I will give you the formula sheet, the definition theorem sheet that so that you don't need to prepare those definition. Okay, other than those, you need to study. But I will provide. Yeah, I will show you later. Okay, I'll put on Moodle so that you don't need to prepare those. User, what do you mean? User friendly exam. I mean, they are just definition and theorem. Yeah. Okay. I think you guys already checked your timetable already. It's in the study week, is it? Yeah. Okay. So happen together with BSc 1, 2, 3. Yeah. Yeah, take together. So same call. Then I think so. MY3 is it? I think so, yeah, big exam. So we can take the same paper. Different paper. Okay. So you need to prove what they use. Yeah. You need to prove what they use. Yeah. So close to the exam time, maybe we will release some tips for the exam. Yeah. Okay. Question? Yeah. Yeah, no problem. This one? Yeah. Uh-huh. You cannot assume. I mean, uh, I realize that when we want to show, we need to show when we want to show the limit exists, actually we are using the differentiability. So might as well like use this one. Yeah. Because there's a term, remember there's a term x plus ya, y plus, okay, x plus ha, y plus hb, and then x plus ha and y plus hb. So when you are dealing with this two variable changing, the way to go from there to the other fxy is actually using this differentiability here. Did you realize this? So to go from this term here, so the key is to go from this term to other term, you just need the differentiability. Yeah, that's the part. I guess that. Yeah. Actually, to unstuck it, you need to use the differentiability. Yeah. Just cannot just deal with continuity. Last time I said just deal with continuity and then pass on, right? Because you are dividing by h. Okay, you're dividing by h. So you can't just use continuity. Okay. So I mean, so if you wonder what I'm talking about, so last time we have this term here. Okay, we have this term here. And then I say I use continuity to make this into fx yhp over h. Okay, but I'm dividing by h, so I can't really do that. I can do it if there's no h at the bottom. I can do this. This is continuity. But dividing by h, remember, you can use L'Hopital or what, but in this case, not sure what to use because I don't know what's my function. Okay, you're dividing by 0. Okay, so you cannot just bring the limit in. This is the step that have problem. Okay, but to solve this problem here is exactly the differentiability. Okay, differentiability help you to split the two changes into one changes, fx and fy. Okay, so this is exactly the differentiability doing. Yeah, and absorb. Okay. Okay. I mean, if you still have question, we can deal with it again. We still have 1 more month to go. So please arrange your times well. Don't leave everything to the last minute to study, okay? And then your exam timing is very good. You know why?
Why?
Huh? Because it clashes with my graduation day. Yeah, so I graduate the same day. So I won't be around during the study week. Yeah, so but you still can message me, email me, but maybe I'll be a bit slow or delayed. Yeah, yeah, where am I?
Oh, so when you want monitoring our examination,
Yeah, but I already asked help from Darren, so Darren will come.
oh, so like this, we can take a sheet of paper, go inside the
What do you mean?
because Darren allows students to take a picture.
Oh, I mean, yeah. So I mean, so we don't bring cheat sheet this time, so I provide the theorem and definition for you in the exemption. Yeah, because it's kind of troublesome. If you want to bring cheat sheet to final exam, they need to apply or what. Yeah. So I directly print for you. Yeah, I print those for you, and then I will show you, and then what you don't need to prepare. You just need to reference and then know how to use it. Okay, the most important thing in this exam, okay, the first tip I want to give you is you need to understand all the proof in my lecture notes, and then understand all the examples, and then do all the review exercises. Okay, yeah, then you'll be good. Okay, I give you the theorem. You need to know how to use it. That's all. All of the question I can for sure. Okay, for most of the question, 70% and above, you will see it before in the lecture notes, in the review exercises. Yeah. That's what I can guarantee you. Okay. Yeah. So anything you don't understand, please ask. Huh? Other than percent, huh?
Right from the proof.
Derived from definition. Derived from definition. Okay. Or maybe you can start think now. Okay. Start and think. Start to think. Okay. Think extra question and ask me. Okay. Hopefully, yeah. Hopefully. I really hope. But maybe still long, but I think it's doable. Okay, it's doable.
Still long.
I mean, not as long. Not as long. Okay, not as long. Not as long. Skip the 30%. Okay. Yeah. Wait, let me find my notes. Okay, so from now, start thinking about the lecture materials, and then any question you want to throw to me, please throw. Okay, if it is exam question, I will tell you answer also, but I won't tell you it's in the exam. So start now, creative think what will be in the exam. Okay, I'll tell you the answer in the lecture, but I won't tell you it's in the exam. Okay, so please think. Any question you want to throw to me, please throw. Okay, so where have we been? Okay, where have we been? Where have we been? Where have we been? Where have we been? Anyone, any idea or not? Where have we been? Spherical and cylindrical. Okay, so we haven't do the exercises. Okay, let's recall a bit what we do. Okay, let's recall a bit what we do. Okay, so we are interested in multiple integral. So how many types of multiple integral we encounter? We encounter double and triple. Okay, double and triple. So double and triple integral. Okay. So double integral, we start with the regular coordinate dx dy. Okay, dx dy. And then triple, we have dx dy dz. Okay. But sometimes in regular setting, maybe the domain become hard. Okay, become very hard. It's exactly like the polar curve example. Polar curve example. You cannot describe a circle just using a line. Okay, you need to split it into two hemispheres. But you can do this in a polar coordinate. Okay, so we turn our question into differentiating, integrating on polar coordinate. Okay, r cos theta and r sin theta. But at a cost. What's the cost to change from regular coordinate to polar coordinate? What's the cost? What's the cost here? We need to introduce an extra r. Okay, extra r factor in. Okay, this is the cost. Okay. So similarly, in three-dimensional case, we have cylindrical coordinate. Okay, cylindrical and spherical. Remember, we can fill R3 using sphere or using cylinder. Okay, who can remember what's the change of variable for cylindrical coordinate? Wait, let me ask someone else. Cylindrical. Okay, wait, let me ask someone. Ryan. To go from regular coordinate to cylindrical coordinate, where you need to send x, y, z to. You send x to where? R cosine theta. And then y to r sin theta, and then z to z. Okay, so this is the cylindrical coordinate. Okay, so if you change this to cylindrical coordinate, do you introduce any new term or not? Do you introduce any new term? Do you introduce any new term in your integral? What is the term? You don't know. Okay, it's okay. Actually, we didn't mention about this last time. Okay, so if you know, that's mean you got do homework. Okay, but it's okay. So we also introduce a term dr. Okay, similar to polar coordinate. Okay, similar to polar coordinate, we introduce an extra term r. Okay, so you can see that cylindrical coordinate actually quite similar to polar coordinate. You only introduce one r. But you also can see that this is really similar, right? Can you see it? The r and theta is only controlled by x and y. Okay, z still remain as a z. Okay, so how should you imagine this? So you should imagine this R3, right? Okay, it's filled out by sheet of R2, and then every sheet of R2 is filled by here. Sorry, circle, lower dimensional circle. Okay, so you have circle on each level, and then filling out the whole R2. And then you use the height to fill out the R3. Okay, so this is kind of like polar coordinate seeking in R3. Okay, the next one is non-trivial. Okay, a bit non-trivial. So this is the spherical coordinate. Okay. So let me ask another one. Mm, 原家, what's the coordinate change from regular coordinate to spherical coordinate? Where do you send your x, y, z to? You don't have your lecture notes with you? Where do you send x, y, z to? Sorry. Huh? Sine? What's that? Sine theta? And then? Sorry? What do I cosine? Theta again. Okay. That's all. Wait. Don't listen to others. I want to listen to you. Then? Do you have lecture notes or not? I was wondering. Do you have lecture notes? You have? Can you find it? Okay, please ready your lecture notes while you are studying. Okay. How about Grace? How to go from regular coordinate to spherical? Oh, row. Uh-huh. Row, sine, phi, and then cosine theta. Okay. How about y? Uh-huh. Sure. How about z? Okay, good. Okay, good. Thank you. Okay, so what do you realize here? What do you realize here? So when you do this variable change, right, you must change from 3 variable to 3 variable. Okay, 2 variable to 2 variable. Because we want to have a 1-to-1 map. Okay, 1-to-1 map. Okay, 3 dimension to 3 dimension. So what are these rho, phi, and theta? Okay, what are these rho, phi, and theta? Well, Li Kai, where does this rho, phi, and theta live in? Hmm. T is what? Angle of what? Angle with z-axis. Okay. And then what? And the line. Okay, sure. So you mean this part is the phi? Okay. Where's the theta? Projection onto the xy plane. With which axis? Positive x-axis. Okay. Okay. So we have rho, we have theta. So what's rho? Sorry, we have phi, we have theta. So what is rho in this case? Where is rho? Is the line? What do you mean by rho is the line? Line is a line. Rho is a number. Huh? It's a what? I mean, row is a number, right? So line is a line. So how is a number is a line? It's a distance. Distance from where? Okay, so it's the distance from the origin to the point. That's the row. So it's the radius. Okay, it's the radius of the line. Okay, so this line here is row. Okay, so where does this row, phi, and theta takes value? 用字哦，用字。So where does row take values? Real number from negative infinity to infinity. Yeah. What do you mean by positive? So what's the endpoint of your interval? Okay, so we just take 0 to infinity because there are positive distance from the origin. How about phi? 0 to pi. Sure, we can put 0 to pi. So meaning what? Meaning we can cover for angle, we can cover from 0 to pi, okay, and then any radius. Okay, all right. Okay, what else we need to cover now? Yeah, so what's that? So we should take theta from 0 to 2 pi to cover everything in our plane. Okay, you should think of it as what? The book. So you can open out the book. Yeah, fully open the book. Then you cover the whole. And then you should imagine the book extend infinitely. Right? Imagine. Okay. Okay. Yeah. Okay. So after introduce this cylindrical coordinate, there's some quite expensive costs here. Okay, we have to introduce. So what do we need to introduce? There's a term rho squared sine phi. Okay, that get extra term rho squared sine phi get introduced into this integral here. Okay, so this is the extra term we need to introduce here. Okay. Okay, so these are, wait, let me see. So, okay, let me rewrite this. Rewrite this integral here. So our integral will become f rho sine phi cos theta, rho sine phi sine theta, and then rho cos theta with an extra term rho squared sine phi, d rho, d theta, d phi. Later we'll see how this term come about. Okay, how this extra term come about, how the r come about, how the rho squared sine phi come about. Okay. Okay, so why we are interested in spherical since this is so troublesome? Okay, so let's say let's see what kind of domain we can achieve. Okay, let's see what kind of domain we can achieve. Let's say I fix rho as a C. You know what's the domain? What kind of domain we can achieve here? If I fix the radius, okay, what's the thing I can get in this spherical coordinate? Qifeng. What are the points you get if you fix the radius? What's radius? Distance from origin. Okay, if you fix the distance from origin, what are the points you can get? Huh? What? Sorry? 0, 0 to infinity. No, I fixed one radius. I already fixed one radius. Fix a number. Maybe it's fixed 2. Okay, what's the surface I get? Huh? Line. No, not line. Not line. How many direction in R3? You have 8 direction. Okay, all the radius with the same radius I take. So what is this object? Huh? Circle. But in higher dimension you get? What do you get? Go up a dimension. Circle go up a dimension. Sphere. Okay, so you get a sphere. Okay, sphere meaning everyone is C from the origin. Okay, this is not quite a sphere, but just take it a sphere first. Sphere of radius C. Okay, how about you fix a angle theta? Okay, you fix the angle theta. What do you get? What's the object you get? Yujing. What's the angle? What's the object you get if you fix an angle C? Theta. Okay, no. Now I fix theta instead of phi. Theta is the one that go over xy plane. So if you fix one angle, what do you get? Don't know. Okay, how about the others? Plane. Okay, you get a plane, right? So over this angle, okay, sorry, this is x, this is y. So my angle should be positive from positive x-axis. So this is theta. Okay, so all these point I get. Okay, so all these line I get it. So it is a plane. Plane with angle theta from x. Make sense or not? All the point on this plane here. So this is a plane starting with starting with x equals 0, y equals 0, forming an angle theta from positive x-axis. Okay. 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 How about the other one? Let's say if I fix okay, what happens if I fix phi? Okay, if I fix phi, what happens? What happens if I fix phi? Also a plane, you sure? What is phi? What is phi? Where is phi? Going. Where is phi?
Yeah, it's from
From
the Z.
Z, right? Yeah, from Z, right? Okay. So phi is the angle from Z. Okay, how do you get a plane? Get a plane. It's the angle from Z. How does the plane should look like? It's a cone. It's a cone. It's an ice cream cone. Okay. So it's a cone. So let's say our angle is in between 0 to pi over 2. Okay. What's this cone here? So this cone here looks like this. Well, every point that is angle between 0 to pi over 2. Okay. Over pi over 2, what happened? Over 2, pi over 2, what happened? Where is pi over 2? Pi over 2 here, right? Okay, over pi over 2, what happened? The cone face downward. Okay, the cone face downward. So if my C, or maybe use another color. So if my C is in between pi over 2 and pi, so the cone will face downward. Okay, so what does this mean? So in your exam, right, if you see this kind of domain, you should consider swapping to this coordinate. Okay, if you see cone, if you see this half plane, okay, if you see a sphere, then you should consider swapping to this coordinate. Okay, maybe you don't have idea yet. Okay, let's do some example. Okay, let's do some example. Okay, let's try some example here. So let's see which one to try. Okay, let's see. How about try this? So let's evaluate this example. Let's do this example. E to the x squared plus y squared plus z squared. So complicated. Okay. But what is this B here? B is the unit ball. Okay, unit ball. B is the unit ball. So which coordinate you think you want to use? Which coordinate do you think you want to use here? You are integrating over a ball, a sphere. Sphere, so become a ball. Hmm? You want to do it regular or not? You don't want to do it regularly, right? So what should you use? So this is, what's your integration domain here? So your integration domain here is this. Okay, so this is a ball. So which coordinate do you think you want to use? Yui. Don't wait for my answer. Don't wait for my answer. Which one? You got three to guess. You got three to guess. Spherical, cylindrical, or regular? Mm. You have three to guess. Don't wait for my answer. Which one? I think I just draw a sphere just now, right? Yeah, under what section? What's this coordinate here? Spherical. Okay, so I think it's probably better to use spherical. Okay, so when we use spherical, right? Okay, how does our equation change? Okay, how does our equation change here? Okay, so one thing you should remember, I think, is this coordinate change formula here. Okay, so let's bring this down. So this is one thing you need to remember, always kind of useful. Okay, so this is the spherical. Okay. Do you know what's the property that these spherical coordinates satisfy? I think I showed you last lecture. You know what does this uh, coordinate change need to satisfy? What kind of property they need to satisfy? These are the points on what object? Sphere. Okay. So if you are on a sphere, what kind of equation you need to satisfy? Addition of okay, addition of the square of your coordinate is equal to what? Is the radius, right? Okay, so the radius in this case, rho. Is it rho? Rho. Right? Okay. Yeah. Okay. So we are integrating from for d rho, d theta, and d phi. Okay. So where are these? How do we pick our integration domain? Okay. How about Siyu? How do we pick our integration domain for rho, theta, and phi? The answer is on the board. So you need to integrate over a sphere, right? Okay. So for this sphere, what kind of radius you need to integrate over? What kind of angle you need to integrate over? How do you cover the sphere using rho, theta, and phi? How to cover?
Rho, I think is
Okay, why is it for rho is 0 to 1? Because the domain is unit ball. Okay, the radius of the point are all from 0 to 1. Okay, and then okay, because you cover the whole xy plane for 0 to 1, and then for the phi, you also go from 0 to pi. Okay. 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 So do you know you can imagine this quite concretely when you go from one to the other variable? Do you know how to imagine this concretely? No? Okay. So let's say how you go from the radius one. Okay. So the radius one, you should think of it as all the point going from radius 0 to 1. Okay. So this is taking radius 0 to 1, right? And then what you do the next? What do you do at the next? You take theta from 0 to 2 pi. So where's theta? Qifeng, where's theta? What's the angle representing theta? With positive z-axis or with x-axis? Which one? Z-axis or x-axis? X-axis, okay? So this means you need to use the theta to go around your xy plane, okay? So you fill up a circle or a disc on the xy plane, okay? You fill this up. And then what's the next? How to get a ball? So to get a ball, you need to go over 0 to pi, okay? So you should think of it like that. Open up, open down, okay? So you get the whole ball. Okay, so you get the whole ball. Is it clear or not? Clear? Can you imagine or not? It's important that you can imagine this domain. Otherwise, it's very hard. Okay? So far, okay? Cheyenne, are you okay? You look confused. Okay? Not okay. Not okay. So you got question or not? Not sure about domain. Is it the question? Not sure about domain. Do you know how to get the radius? Are you okay with getting the radius? How about theta? Not sure how to get theta. Okay. So theta is what? Theta is the angle from the x-axis. So this is theta. XY plane. Can you imagine XY plane? And then yeah, so the angle is representing the angle from positive x-axis. Okay. So now we are taking 0 from 0 to 2 pi because all the point on this xy plane we need it. So all the angle from positive x-axis, we need all these points. Because this is okay, can you see that this circle here is a what? Is okay, so if you cut this sphere using xy plane, you get a circle. Can you see it? So this 0 to 2 pi is representing this 0 to 2 pi. The whole circle, the whole disk, not just circle, disk. Because we take a ball, not a sphere. So everything inside is sphere. Okay? Okay. And then to get phi, do you know why we take 0 to pi? Because we need to fill up the whole ball. Up to this stage here, we only got a disk. Okay? To fill up this, I need to include the positive hemisphere and the negative hemisphere. So I need to take all the point that make up phi from positive z-axis. So let me fill this x, y, z. Okay. Make sense? Okay. Okay. Question? We'll finish this, then we will take a break. Okay. Can follow or not? Can follow? Okay. So we're done with this. I think the really hard part is about this domain here, changing the domain here. But after that, so how to go from XYZ to rho theta phi? You need to use some identity. Okay, you need to use some identity here. So one of them is this radius identity. It's very useful. The rest is about tangent or trigonometry. Okay, so the most important here is this one, this guy here. Okay, so that's why you will see this long bit coming out, x squared plus y squared plus z squared. Okay, so we can replace this x squared plus y squared plus z squared. Okay, so Michelle, how we change this function here? Okay, how do we do that? How do we do that? What do we get? Yeah, what do we get? Do we get e to the of 2, and then to the power 3 over 2. Okay, good. So is that all? Is that all? No? Okay, we'll so say no. Hey, where's Suoning, huh? Suoning? Gone. Okay. So what happened? What are we what do we still need? Whole square, sine, theta or phi? Okay, so can we integrate this or not? Looks a bit horrible. Okay, so can we apply Fubini or some sort? What can we do? What can we do? What can we do to this integral here? Huh? Mingxiu? Okay, we can split it into different variables because these variables are separable. Okay, let's split it into phi, theta, and rho. Okay, so with respect to phi, we got the sine phi. Okay, with respect to theta, what do we have? We have nothing but 1. With respect to rho, is this e rho cube rho squared. Okay. All right. So, what should we do? What should we do? So the first integral, what do we get? We just get negative cos phi evaluated from 0 to pi. And then for the next one, we just get 2 pi. And then the third one, how do we do this? Any idea? How to integrate e to the rows cube times rho square? Do substitution, is it? Okay, do substitution. So u equals to 3 rho cube, and then du equals to 3 rho square d rho. Okay. All right. So what's this here? So this becomes 0 to 1 of EU du over 3. Okay. Okay. So I think the next should be straightforward. So we got 2 pi, and then differentiate this, we got EU again. Okay, EU. 0. Okay, so all together we get Jingbo, what do we get? The end. So you have to close this up. Wow. Are you really quick of 4 3 5 and then? Okay, good. Yeah, this is the answer. Okay. Yeah, if you want final answer, right, you should look for Jingbo. He might not know what's going on, but he knows the answer. Not just a joke. Okay. Any question before we take a break? Okay, let's take a break until 3 2 3. 3 2 3.现在网 OK 啊？好像
OK，
没有诶，他还不 OK，
我
他不给我进
一直都 OK。
是吧？就你吧。OK，等一下，你问啊，你问，我调这个先。呀，
就是我感觉你放这个那个圆柱的那个
圆柱
的那个坐标里，
对，
它那个 z 它是不会受到 xy 控制到，就是 z 是一个单独的，
没有错，没有
但是
错。
它这个 integral 的时候，它这个 z 换成一个关于 r 的一个方程，
嗯哼，
但是怎么换过去的？
你说这一个啊？
对，
你说这一个啊？
对，把 z 换成了一个 integral z 的时候，换成一个关于 r 的。
那跟我们刚才做的那个东西没有关系啊。
这跟我们刚才做的没有关系
啊然后
跟之前的那个上节课
对，
对，
就是怎么说呢？
就是它这个 z 跟这个 r 是没有关系，
所以呢，
所以你这样 integral，但是感觉我不是很明白这个，就是
我不是很懂你在问什么，现在给我讲一下。不是很懂你在问什么？
就是我不是就是我不是很懂后面这个就最后的一个 integral，它是什么理？
第一个这是最先的，先到外，先到后，先是在里面。
对
，OK，所以你是说你不懂这个在干嘛？
嗯，
但是这个没有什么，我只要把这些全部换掉都可以，你懂什么意思？
就是从 theta 开始往前，
不是，我是说，就是如果把它换成 xy z 也是行啊，这个整个东西都行。对啊
但是这个 z 这个跟 z 的和 x 没有关系，
，x 跟 z 没有关系，对，没有关系啊，没有关系。
那我们可以 integral。
OK，我看一下啊，你给我看一下。OK，我知道了。OK，它这个 z 哦是被你的 radius 和 theta 控制。OK，但是在 change of coordinate 的时候，它是没有被他们控制的。它这个是因为你的 integration domain 的原因。对，
那我的 integral domain 它为什么可以换成跟那个 xy 有关的一个？
因为为什么哈？给我想一下啊，因为你给我想一下，因为OK，先看一下这个在干嘛？这个是 其实我想 skip 这个，其实 OK，这个他在说什么？这个他其实是在找这一块 rectangle。
对
，OK，所以怎么找这个 rectangle 呢？他从 θ 开始做，OK，他 fix θ 先，因为 θ 很容易嘛，θ 就是哪一个角它那个角度嘛，
对
，OK，fix 完这个过后呢，你就可以开始找你的 dr 和 dz 了，OK，其实你可以交换了，你可以交换 dr 或 dz 或 dz 或 dr，但是他现在先 fix 他的 dr 先，OK，意思说我要从哪里 integrate 到哪里，在 radius 那里。OK，从这张图里面看到的是，它是从这一个点到这个点。
对
OK，所以你怎么形容这两个曲线呢？这个两个方圈，它就用 θ 来告诉你了。怎么说呢？就是在这个 θ 的时候，它是在哪一个 radius？在这个 θ 的时候，它在哪个 radius？在这个 θ 的时候，在哪个 radius？然后这个也是，在这个 θ 在哪个 radius？在这个 radius，对不对？
对
OK，然后现在下一步呢，它要告诉你它的 z 是什么了。那怎么知道这个东西的高度多高呢？每一个点我都要告诉你多高。当你在讲每一个点的时候，这边每一个点都有 θ 跟 r， 所以就你给我一个 r， 你给我一个 θ， 我就知道什么 z。对，被r 跟 θ 分封，就这样吧。呀，就这样吧。就这样。I mean， 你可以交换的嘛，其实你也可以先决定 θ， 后再决定高度，然后再决定多长都可以。你也可以决定高度先，再决定都可以，都行的，换来换去都行。所以
那这个是不是也可以换成
哎
XY？
可以啊，可以。它这个东西是从 XY 过来的，所以它才这样子。
因为 XY 的话，你就会直接拼凑到 Z 的时候，就不需要再练习发克，也换成 XY，对，这个坐标系就不用这个，不用这个抛的。
没有，因为有时候有时候你看这种怪怪的，这种不是正方形的，不是长方，不是正长方形的东西，不是你用这种你就可以形容出这个曲线了。如果你要形容这个曲线在正常的那个正方形，你会有什么 square、s square、y square 这种东西，所以你要拿 square root，然后你要 integrate 这些东西哦，你知道吗？你要 integrate square root 这些东西，所以就比较难啊，就是 I mean 看它的形状是什么，就比较容易 integrate 啊啊
好难算呀！
好难算
都难算。
对 I mean 看多一点，要做多一点力，对呀。
公式如果就是我自己画出来的话，它会有点不一样啊。就是我的 cos 跟 sin 它会调换。
哦，OK，
然后变成说，我的 phi 0到 π，
你 I mean 这个等一下我们会讨论到这个，就是 change of variable， 你要 change of 你的 transformation 只要 one to one
然后会多加一个 R，还有那个什么
phi sin square，
加这些个
怪的
这个都是Jacobian，
那个是Jacobian，那个是 Jacobian，那个是 我的东西
determinant 是吧
那个是 对，那个是对，没有，我只是想要指出这个是 Jacobian，所以但是你这样子变来变去好像
只是我这边的 Jacobian 会不一样，Jacobian 会不一样，然后你这边
对，但是我想说你这个可能没有差，有差没？
没有差，
应该没有差，
一样还是可以 separate 的，
应该没有差，应该没有差。
只是我 domain 会不一样，然后
domain 不一样。
然后画这个给你，
我觉得你切口边应该没有变
我画这个给你没有问题的。X
，yeah，你这个就是有一点像是你又做多一层，就是你从 cos 跳到 sin 这样，是不是？
还不止哦，你看吗？还有吗？我看一下，哦，你是 cos 去 cos sin，我看一下 cos theta，哦，你整个反掉
啊，我的 x y 会反掉。
啊，可以咯，就是方向不同哦。
对对对，
呀，方向不同啊，方向不同啊，对，
因为这样子我就不用特地去背公式。
可是你要小心哦，你就要小心哦，你就小心不要做漏哦。你要小心，你不要做漏，你不要选漏哦，或者你不要选多，你选多的话也是不能哦，你懂吗？本来0到 infinity 可以 cover，然后你忽然间又选到减 infinity，然后这样你就做多了。
对哦对哦。
对，你就做多了，你不可以做多 ，1 to 1跟 on。之前要到了，要到了。对啊，会快的还是慢？快的还是慢的？OK。Okay, let's see another example, right? Let's see another example. Yeah, let's see another example. Okay, so let's see another example. I think this example closer to your assignment question. Hey, have anyone tried integrating using regular coordinate for the assignment question? There's a square root thing, right? A lot of square root. Did you try using just integrated over square root? Did anyone try it? Assignment question 4. Oh, question 4. I know. I mean, you can use quadratic. I mean, does anyone just integrate it using square root or not? Maybe you can try if you are brave enough. Okay. Yeah. Okay, so let's check this. Okay, let's check this one. This one. Okay. So this domain here. So how to integrate over this guy? What's the whole thing here? Okay, so when the first thing you see integral, multiple integral, right? Try to sketch the domain first. What's the domain here? What's the domain here? Z dy dx. Okay. So dz dy dx. So which one is get fixed first? Dx, right? Okay, the outer one get fixed first. So let's draw this, try and draw this domain here. Okay. So your x direction is fixed by -2 to 2. Okay, -2 to 2. Okay. Okay, so how to figure out what y you have? What y you have? What are the y you have? Okay, so maybe you just check from these two endpoints first. What do you get? Qifeng, what do you get? At these two endpoints. So at -2, what are the endpoint of y? Yeah, y is going from where to where? Okay, so let's write down this domain. So x is going from -2 to 2. Y is going from square root -4 minus x squared to square root 4 minus x squared. Z is going from square root x squared y squared to 2. Okay, so where's your y bound by? when x equals to -1. Yeah, -2, sorry. So when x equals to -2, where are your y? Sorry? Y is equal to 0. Because y is bounded above and below by 0. Okay? Similarly, you can check for your x equals to 2. Okay? So maybe let's pick some other point. Okay, let's pick x equal to 0. Yeah, x equals 0, what do you get? Venus. Venus. Yeah. So when x equals 0, y is bounded by what? Any idea? I mean, you need to sub your x equals 0 into these two bounds. When you sub x equals 0 to these two bounds, what do you get? Your y is bounded by function in x. Can you see or not? Yeah? Any idea? Sub the x equals 0 into the bound. Substitute x equals 0 into this bound. What do you get? The bound for y. Yeah. Yeah. So when x equals 0, y is bounded below and above by what? Negative, bounded below by -2 and bounded above by 2. Okay. So when x equals 0, you get the cross section from -2 to 2. Okay. How to fill the rest? How to fill the rest? Okay. So can you notice that this is actually a positive hemisphere and negative hemisphere here? Okay. Because can you see that these points actually satisfy equation? So let's say square root 4 minus y squared is equals to y. What do you get? This is the outermost. You actually satisfy the point y squared equals to, sorry, this is x. Yep. Start. Okay. Okay. Hey, what? Not presenting. Yeah. Okay. Yeah. So this point actually satisfy a equation of circle. Okay, equation of circle. Like that. Okay. 4 minus x squared. Okay, equation of circle. So all these points here are equation of circle. Satisfy equation of circle. Okay, so you got everything inside here. Okay. So when you sub different x, you get a different yeah. So you get, I mean, you consider all the radius that is in between -2 and 2. Okay, so you fill up all the circle. Can you imagine or not? Imagine. Okay. So how about Z? How about Z? What happened to Z? What happened to Z? What happened to Z? Let me ask Jiangcheng. Jiangcheng. So at x equals to 0, y equals 0, what happened to x? What happened to Z? Z is bounded by what? Bounded above and below by what? Any idea? Huh? Bounded below by? Sorry? 0. And then bounded above by 2. Okay, good. So if you look over the origin, the Z you cover is 0 to 2. Okay, from 0 to 2. Okay. So what about the rest? What about the rest? Okay, what other point we can try? What other points you want to try? So these are the X, Y that are allowed in your circle here. So what other points you can try? Let's try. What other points you can try? Eating. What other point you can try? What other point on this you can try? Try and give some point on this. Idea. 1 1 1 1. Can, sure. 1 1. 1 1 lie inside here. Okay, this is something inside the interior of this. Okay, sure. 1 1. Maybe I want to try something on the boundary. What are the points on the boundary? 0 2. 0 2. So where is 0 2? 0 2 is here. Okay, 0 2 is here. So 0 2. Okay, sure. Okay, let's try these two numbers here. So 1 1, what do we get? At 1 1, what's this Z bound by? Jiawen. At X Y 1 1, what's this Z bound by? Bound by what? Square root 2, bounded below by square root 2, bounded above by 2. Okay, good. How about at the boundary point 0 2? Okay, what's this Z bounded by? Zhe Xian. Huh? Bounded above by 2, bounded below by what? Wait, don't kacau him. Don't kacau him. So bounded below by? Cannot see, huh? Zoom. Okay, bounded below by what? Yeah. So what do you get? 2. Okay, so you bounded below by 2 as well. So this means Z equals to 2. Okay, so what can you see? So you can see that when you go away, okay, to the circle, right, the height reduce. Okay, so at the origin, you got the full length 0 to 2. And then when you go to the interior point, you only have square root 2 to 2. And then until you reach the boundary, you get 2. Okay, what's this shape here? What's this shape here? So you reduce. You can check that it actually reduced, right? What is x squared plus y squared? Is the length of your point, okay, in the disk. So when you go further out, right, this length will increase. Okay, increase until it hit the maximum 2. Okay, so your bound becomes, the interval of your bound becomes smaller until you reach the highest 2. Okay, so what's this shape here? What's the shape? Sector. Sector. I mean, higher level sector. I mean, can I say that? Maybe I can say that. Yeah. What's that? You need to have 3-dimensional shape of this. What's this? Not sphere. Not sphere. What's this? What's that? What's that? What's that? Ball. But we got a sharp end here. So it's a con. And we got a con here actually. So we got a con. Let me see if I can do it better. So we get a con. Wait. So we get a con. Okay. So I get a con here. Okay. So when you go outside the Z bounded, the interval for Z decreases. Okay. Okay, until you reach the maximum length. So this is a con. All right. So what to do here? Yeah. Yeah, I mean, this is the primitive way. And then maybe you, with more experience, once you see this equation, you will know that how it changes, then you can deduce from there. Otherwise, you really need to check how this interval change. If the shape too familiar. So, I mean, this is one part of this course. So maybe we won't give too hard shape unless
basically the shape we know just like
That's right. That's right. Yeah, that's right. Yeah. Yeah. Okay, but the problem is how to turn this into a useful coordinate to integrate. What kind of coordinate can describe the con? What kind of coordinate can describe con? What kind of coordinate can describe con? Cylindrical. Cylindrical? So how? How to use cylindrical coordinate to describe con? I think we also introduced this con, right? Actually, you can use spherical also. Okay. So let's say we use spherical first, okay? Let's say we use spherical first. How should we integrate? How to describe this con using spherical? Let's put d rho, d phi, d theta. Okay. How to describe the con? What's the rho? What's the rho? From where to where? From 0 to 2. Okay. And then how about phi? Phi is what? Direction from the positive axis. Okay, so what's this angle here? Do you have angle here? 0 to pi over 4. How do you find pi over 4? How do you find pi over 4? Huh? How do you find it? I think this is a pretty important question. So how do you find this angle here? How do you find this angle? Start again. Start again. So this angle is what? Let's try it. Okay, let's try it. So this is angle phi. Okay. Can you find a right angle triangle here or not? Okay, so what's this right angle triangle here? The radius is 2. Okay, how about the hypotenuse? What's the hypotenuse? What's this slanted height here? Do we know? We just need the height is enough. Okay, use tangent, is it? Okay, we also can use tangent. Okay, so 2 over 2. Okay. So tangent of what angle is 1? So this is implied, this is pi over 4. Okay, so we're going from 0 to pi over 4. Okay, so we settle phi, we settle radius. Have we settled theta or not? So what's theta? 0 to 2 pi. Okay, good. Okay, so this is one of the way you can solve it. So you can use this way. Let me see. So what's our function here? So our function here is x squared y squared. So I think kind of hard to go from just x squared y squared. Is it hard? Hard or not? Because the only relation we know is r squared. Sorry, yeah, r squared rho squared equals to x squared plus y squared plus z squared, right? But here we only have x squared y squared. Okay, so meaning we have an extra coordinate if we want to use this. Okay, yeah. So how? So how? Okay. Maybe we can try cylindrical. Okay, try cylindrical. Okay, how does cylindrical work? Can we use cylinder to build the cone or not? How? Interesting. No, you just put into the sharpener, isn't it? Put into the sharpener, right? Okay. You just put into the sharpener, then you can make out the cone using cylinder, isn't it? This is how the pen works, right? Okay. So how to do it mathematically? Okay, how to do it mathematically? So let's bring out the cylindrical coordinate first. Cylindrical coordinate. Okay, so we have 3 of them. One is dz, dr, and d theta. Okay, so let's decide what is theta first. Okay, theta I think is easy. It's just 0 to 2 pi because we want the whole circle. Okay, 0 to 2 pi. So we start from thinking about cylinder first, 0 to 2 pi. And then what's the radius? What's the radius of cylinder? In our case here, radius 2. Okay, so we go from 0 to 2. Now is the place where you need to do the sharpening. So how to do this sharpening here? At the origin, what's the radius? 0. Okay, and then you increase all the way up to 2. Okay, how you increase? Actually, you want to say something? Okay, actually how you increase here is going from square root x squared plus y squared to 2. Right, this is the bound here. Remember the bound for your z. Okay, this is the bound. But in this case, this part is what? Okay, so this is just r. Okay, so it's from r to 2. Okay, make sense or not? Does it make sense? Make sense or not? Does it make sense? Okay, so let's turn the other way, study the other way, right? Okay, the other way we have theta. Okay, theta going from 0 to 2 pi. Okay, you got a circle. And then radius from 0 to 2. Okay, radius from 0 to 2. Okay, actually you got the whole cylinder here. But the key part is the last part here. From this r to 2. Okay, radius r to 2. Yeah. Yeah. Make sense? R to 2 here. Okay, so this represents the height. So this height is only positive. Okay, so that means we remove the negative part. Okay, but how does this change? How does this change? Okay, how does this change? This R here depend on my xy. Okay, so when my xy is lying at the origin, I get a I get 0. Okay. And when my xy go away from origin, okay, the length decreases. This is exactly what we computed here. Right? This is what we computed here. If we pick something from the origin, we get the whole interval. If we get something in the interior point, we get something less. And then when we get something from the boundary, we get the number 2. Okay. Okay. So so at the boundary, we cut at 2. Okay, so we cut at 2. So we cut at 2 here. So so on the boundary, we cut at 2. Okay, and then for the rest, we have this height change. So it's the cone that we want. And follow the construction or not. Okay, if you don't fully understand, that's fine, but you need to at least know what you need to do. And then you try and look into why it is true. Okay, can follow the instruction. Can you reconstruct the cone using this interval here? Can you reconstruct the cone using this domain here? Both you need to be able to do. Okay. These things of course need practice. Okay, this doesn't come naturally, so need practice. But at least you should know what you should do. Okay. Okay. Is it Wei Zhe? Who is Wei Zhe? Oh, Wei Zhe is there. Okay. Who is the one sitting in front of Ryan? Yeah, you. Yeah. What's your name? Oh, see it's okay. See it's okay. Are you okay or are you confused? Confused? Not confused. Okay. So cylindrical coordinate. Okay. So what happened to our function here? Okay. So what's the Jacobian we have? We have R. Okay. And then what happened to our function x squared plus y squared? So x squared plus y squared become just R as well, right? Because in cylindrical coordinate, what do we have? We have x equals to r cos theta, y equals to r sin theta, and z equals to z. So x squared plus y squared satisfy the equation equals to r squared. Okay. Okay. So these are the identity you need to remember. For example, tangent theta also you need to know. It's just y over x. Yeah. So this is a set of equation you need to know if you use cylindrical. Okay. Okay. So now you need to differentiate, integrate r squared. Okay. So do you know how to integrate r squared? Okay. So now the time is for Jingbo. So how to integrate this?
It's time.
How to integrate this? How to integrate this? Just integrate. Just integrate. Okay, so can we split off some of the integral or not? Yes, right. Okay, which one we can do first? There's nothing. Okay, the other one. So there's nothing depend on theta. Okay, so theta, we can split the theta off. And then the other two should stick together because z is depending on r. Okay. Yeah. So we got 2 pi. Okay. Integrating r squared with respect to z, what do you get? Integrating r squared with respect to z, what do you get? R square multiplied by Z. Huh? Isn't it? Correct or not? What are you saying about? What are you talking about? The first one. This one? Second line. First line.
Why is it R squared?
Why is it R squared? R cube. Oh, okay. Sorry. Okay, so here is the square. So we got cube, correct? Okay, good, very good. Yeah. Okay. So we integrate R cube, we got R cube times Z, correct? So Z is integrating from R to 2. Okay. So we get 2R cube minus R to the power 4. Okay, dr. Okay, so how to integrate this? I think you are good for this. We got this. Please check, please check whether my integration correct or not. Okay, please check. Okay, and then all together we get, that's, so simple, you get 16/5 or not? Okay, yeah. So you just do the usual computation, you should get 16 pi/5. Everyone check? Correct. Okay. Okay, why you say correct, then correct. Okay. Okay. So before we finish, right? Before we finish, not finish for the day, finish for the break. Let us introduce a new stuff. Call this change of variable in multiple integral. Okay. Yeah. So what are we doing actually? What are we doing? Going from regular coordinate and then spherical and then cylindrical. Okay, what are we doing? So we are doing a transformation here. Okay, this transformation is really the linear algebra transformation sense. Okay, this is the transformation they talk about. So the transformation we care about here is a one-to-one and onto. Okay, transformation one-to-one and onto. Okay, because we need to be able to go forward and go back. Only this way we will get the same number. Okay, only this way we will get the same integral. Okay, we need to be able to go back and forward. So let me write down. So this is a one-to-one and onto map. You guys know what's a one-to-one and onto? Injective, surjective. Okay, one-to-one meaning everyone pair up with one. Okay, and then onto is everything in the codomain, get mapped by a pre-mesh. Okay, very good. Okay, so should we do this exercise or okay? Let's keep going first. So let's say we got this T one-to-one and onto map. Okay, using the map, the following map. Let me highlight it. Okay, this is the map. Okay, what is the kind of such map? So for example, just now. Okay, let's see what are we doing just now. So just now, what do? We send the coordinate xy to the polar coordinate. Okay, this is, you can prove that this is a one-to-one and onto transformation. Use theta. R sine t. Theta. Okay. Similarly, you can extend this to three-dimensional, right? Just now. We have two kinds. So one is a spherical, the other is a cylindrical. Okay. And then what's the theorem here? The theorem here is when you want to change the integral to the other coordinate system, you multiply by this Jacobian. Okay, this Jacobian here. That determinant of a Jacobian. Okay, so what's Jacobian? So we talk about this Jacobian here. What's Jacobian? Jacobian is taking all the possible combination of your partial derivative and then arrange it in a matrix form. Okay, so what does this mean? Okay, so what does this mean here? Okay, so let's say this Jacobian of UV, okay, this Jacobian of UV. So you define define xy in terms of UV here. Okay. Let me see here. Yeah. Okay. So you go from xy to UV. Wow, this question, I think, let me see here. I think something wrong with this map here. So I think this map, okay, let me don't deal with this map first. Okay, so what's this Jacobian here? So you need to consider all the possible you need to consider all the possible partial derivative. Okay. So for example, what? For example, you have two variables on one side. Okay, let me write something here. So you have two variables on one side and two variables on the other side. You need to consider all the pairs. Okay. You need to consider all the pairs. Okay. So let me think how to say it more precisely. Let me think. Yeah. Okay. So I think I show you an example. Let me show you an example. Let's talk about how this formula comes from. Which one? Okay, it's not here. So maybe let us do it. Let's take an example. Okay, actually it's this one. Okay. So let's take this as an example here. Okay. So we want to show this. This is a regular coordinate. Okay, this is example regular coordinate. We want to turn it into a polar coordinate. Okay. Okay, so what's the formula given there? Okay, the formula says that the function will become, okay, will become what? Will become, so let us do the t first. So what is our t in this case? Okay, what's our t in this case? Yeah, so what's the transformation in this case? Okay. So our t should take from r and theta go to r cos theta and r sine theta, where this is just x and y. Okay. Okay, so after change of variable, what happened to our function? So our function becomes something in r and theta. Okay, multiplied by something we call the Jacobian. Okay, determinant of the Jacobian. We call the matrix Jacobian, and then we take the determinant. Multiplied by dr d theta. So in this case here, this is r and theta. Okay, so the problem here now is, what is this Jacobian? Okay, what is this Jacobian here? So note that, first of all, this Jacobian, right, is a square matrix. Why is it a square matrix? Okay, because you are taking all the variable, okay, and then differentiate it with the other set of variable. Okay, so like what I said just now, transform one-to-one and onto transformation, right? You need to go from the same number as the set of, go between set that has the same cardinality. Fair enough. So in polar coordinate, we have x, y go to r and theta. But for cylindrical coordinate, we have x, y, z go to phi, theta, and rho. Okay, so we need to go because it's a one-to-one and onto map between vector spaces, so the dimension must be the same. Okay, so this matrix, first of all, is square matrix. So what's the entry inside this matrix here? What are the entries? Okay, these entries are partial derivative. Okay, so what sort of partial derivative you need to consider? You need to consider all sort of partial derivative. Okay, but how do you arrange this partial derivative? How do you arrange it? How do you arrange it? Okay, so you should arrange del x. So you should arrange the first variable on the first row, second variable on the second row, and then the one that you differentiate with respect to put as the same row. Okay, so what do I mean by that? So for example, your image is x and y. Okay, your image is x and y. So you need to differentiate your image with respect to the variable in your domain. Okay, so you should consider del x, del r, del x, del theta, del x, del y, del r, and del y, del theta. Okay, so it also makes sense, right? Because x is equal to something in r and theta. Okay, so you can do the partial derivative. Okay, so how do you arrange this? So for all the del x, you should put on the same row. Okay, and then the thing that you differentiate with respect to, you also arrange as a same column. Okay, so for example, del x, del r, del x, del theta, and then for the bottom row, you put del y, del r, and del y, del theta. Okay, so you arrange the function from your codomain in a row, okay, and then arrange the variable in your codomain in a column. Okay. Okay, row and column. Okay. Okay or no? No, okay. Let's try another example. So let's do a higher example. Try one more example. Okay, let's say we have a function going from phi, theta, and phi to x, y, z. Okay. So what's the Jacobian of this transformation here? What's the Jacobian? So first you need to consider all the partial derivative of your codomain with respect to the domain variable. Okay, consider all of them, all possible way. So how many possible way here? How many possible way? 3, just 3. I mean, all the possible partial derivative you can get from this 3 times 3. Okay, you got 3 times 3 because every variable you could have 3 possibility to differentiate over. Okay, so you got 3 times 3. So Jacobian matrix is a 3 by 3 matrix. Okay, so how do you arrange your Jacobian matrix? How do you arrange? Okay, so you arrange your function from the domain as a row. Okay, so you have del x, del y, del z, and then del x, del y, del z, and then del x, del y, del z. Okay, so what do they have to differentiate with respect to? Okay, so we arrange the variable from the domain in a column. Okay, so the first column you have differentiation with respect to row, for example, and then second variable you can with respect to theta, and then so on. Maybe you can exchange row and column. I think it shouldn't be a problem. You exchange row and problem, I think you still get the same determinant. Is it true or not? Not true.
Absolute value.
Absolute value. Oh yeah, okay, yeah, okay. So you will introduce a sign change, right? Because if you interchange column or row, I think you interchange row, you will get a sign change in your determinant. Yeah. There are three basic operators in your linear algebra. Yeah. So one of them will introduce a sign change. But in the like what Sui said, you see, there's a absolute sign here. Okay, so this absolute sign will take care of the negative sign change. Okay, yeah. Okay, yeah. So let's go into this definite example here. So let's see what do we get. Okay, so what do we get out of this determinant here? Okay, in this case here, we are differentiating r cos theta with respect to r, differentiating r cos theta with respect to theta, differentiating r sine theta with respect to r, and differentiating r sine theta with respect to theta. Okay, so what do we get for this matrix? Okay, so the first one we get cos theta and then minus r sine theta and then sine theta and then r cos theta. Okay. So what's the matrix of this? What's the determinant of this matrix? R cos square theta plus r sine square theta. So you get a r. Okay, so that's why in polar coordinate you have an extra r outside your function. Okay, so you have an extra r outside your function. Okay, similarly you can show it for cylindrical coordinate. And spherical coordinate you got rho square sine phi. So also coming from this giant determinant here. Okay, yeah, question. Where? X and then column row. Column X 3 by 3. Column X and then column. Oh, okay. Yeah, right. You are right. So this should be row. Yeah, you're right. Okay, good. So here is X. Yeah. X. Yes. You mean this, right? Yeah, okay, good. Yeah. Yeah. But if you exchange it, it's a transpose, right? So is it transpose or not? Not quite transpose. Actually not transpose, or I write something repeated, isn't it? Just now. It's a whole row, is row X over row. Yeah, it's not transpose. Okay. Yeah. Okay. Okay, later we'll come back and do one example of this, which is not spherical, not polar, and not cylindrical. Okay. Yeah. Let's break until 4:20. 4:20. Huh?
嗯，然后第一个例子，
对，
就是那个第一个例子，那个肉的善 A 我
哪一个？
我们第二个小时讲的第一个例子，跟那个 Simon 的比较像。
OK，有看一下在哪里啊？你是说你不知道怎么画这个 con？
不是我就是我它这个肉，我不是很理解。
你说这个 sphere？
不就是肉
这个肉
汉
这个肉哈，看一下啊，在干嘛？在干嘛嘞？对，我是 theta 是0到2派，and then 我是从0到 pi over 4，没有0到 pi over 4是这样，这个是长度，到 pi over 4，然后有整圈，然后这个 row 是从0到2派，对呀，不对吗？你看，我是一圈嘛，我有一圈，and then 我有这个角度了，这个角度加上一圈，这样我是不是有那个无限的空间
这指的是什么可能 ？X 该类可能。
？OK，我比看，地大是这一圈，OK，
对，
然后0到4拍的话是这一个角度吧，对不对？这个
是
角度，但是这个角度我有一整圈，然后这是无限嘛，因为我还没有告诉你它 radius 是哪里嘛，对吧？所以这两个的时候，我只告诉你了，我只告诉你什么呢？我只告诉你这些圈，是不是画到很乱？
它这个 Z 不是小于等于2吗？
它的 Z 是不是小于等于？对啊，
对，所以就没有不像。
对，
到
对，所以下一步我们就要决定它的 radius 哪里到哪里。对，我们下一步要决定。
我觉得这个，我觉得应该2的更好。
哪个？2的根号？
对
，2的根号。
2乘以2的根号。
2乘以2的根号。OK，我们可以查一下。所以你是说这个 ray 是这个哈？
是。
对，这个刚才我们没有算到，这个是什么啊？其实它不是2，它是什么？哦，对，因为是2，我们知道这个2跟2了，所以是224加224，所以是对，没有错，对，你对，没有错，你对，没有错，
哦，对，
没错，耶，没有错，你对，
就是这个问题。
，yes，
先讲不要对不对？
哦，OK，
因为你讲这东西没有办法变成中文。
就会有漏一些东西，是吧？
要离开的蛮多的。
马上要看你双上点还是情况这样子，还是什么都是。
来看
这个我
对，
我是需要一个 I 大于0的条件，需要解释啊。
需要解释，解释得出吗？对不对？应该要，没错，没错。
是因为
是 I，
我们这个平时的。
先知道就那个，因为如果它是像这样的话，这个所有的做表转换都是一样。我有点看，如果有这个
linear 是只是一部分吧，因为你把它这一掉就好。
linear 好像用 cylindrical 做更快哦。用 cylindrical 做更快。
我又看到一个更快的。
怎么呢？
没有，就 I2乘以1，我可以写这个。
啊，对啊，对啊，那个 degenerate 对啊 degenerate 也可以，好像也是，都可以。OK，因为但是我一开始想这个时候是在玩那个了，都可以，都可以啊，都可以。
然后我发现我用那 S 乘以1也是要解释，诶，不能冲，就
哦，
因为 S 等于派那里，我记得你没有解那里为什么大于？我就来。
我是问 volume 呢？你问 volume 那我听不了。对啊，我没有问 volume，我只有用到这个。对。但是也是要，因为你要界定这个。对对对，它不可以是零啊，因为它是一个。呀，对对对，还是要，对对，就是。Okay, we got Venus, 韦泽、思雨、顺灵、凯仁、金波、齐峰、华英、Ishan not here, 英奇 here, 何怡 here, okay, 雪燕 here, 江晨、江晨 goes you, yeah, saw you, yeah, I got you, yeah, I got you, I just take attendance, yeah, 家业 here, 李凯、袁家、文硕、一定、玉为、燕博、OK， 陈烨、林金、董杰、玉金、周、应宇、柳晴、真诚、硕宁、武力。哎，陈烨 ，you normally sit with 硕宁 right? Where is he? 啊？Oh, yeah. Nanso is sad or he is sick? Huh? Sick. Okay, okay, okay. Okay. Jing. Hey, Yanjing successfully changed your degree, is it? Okay. Transfer degree. Okay. Congrats. Bye. Congrats. Yeah. 子倩、德谦、莹莹、Grace、彩叶、嘉文、明秀、Michelle、Ryan、Ellie、永志、雪梅。Okay, good. Okay, let's start.
Okay, let's start. Yeah.
Okay. Consider this integral here. Okay, integral of cos x minus y sine x plus y dA. Okay, over a rectangle. Oh, sorry, triangle. Triangle with 3 vertices. Okay, 0, 0, pi, minus pi, pi, pi.
we pick a point that is irrational. Yeah, irrational. Pi minus pi and pi. Okay. So what can we do? Okay, what can we do here? So we can consider a transformation. Okay. So really what we're doing with transformation is like a bit like substitution actually. Substitute. Okay. So what kind of transformation we can consider? So there are two variables here, right? Okay, so we should consider variable change from 2 to 2. Okay. So how to make this integral easier? Yeah, so if you can replace something inside with something easier, then you can integrate cos and sine easily. Okay. So one natural things to think of is u equals to x minus y and v equals to x plus y. Okay, this is the things you can consider. Okay. So is this 1-to-1 and onto or not? I think you can show it is. Okay, you can show that it is 1-to-1 and onto. Okay. One way to check, right? One way actually to check is you can see that these two are not scalar multiple of each other. Right? Because this is two variable case, it's easier. Okay, as long as it is not scalar multiple of each other, then they are linearly independent. Okay, linearly independent. Yeah. Okay. Let's see what does this map do to our domain here. Okay, let's see what does this map do to our domain. Okay. So for example, we can see what happened to our endpoint. Where does our endpoint go? Okay, under this map, what happened to pi minus pi? So under this map, what happened to our t? So be careful a bit. Should I say something detailed or?
I think
Yeah.
you-
Question?
the first one should be pi, right?
Yeah, pi, yeah. Correct. Yeah. Okay. Let's follow the notation we have just now. Okay. So just now, what do we have? We have t from uv to xy. Okay. uv to xy. So in this case here, what is our xy? Can you find what is xy from this transformation here? What is xy? Okay, u plus v divided by 2, and y is v minus u over 2. Okay, you can do substitution, you can do what's that? Row reduction. Okay, anything you can do to find this. Okay, so this is our map here. Okay, so to check where this xy gets sent to uv, we need the inverse map. Okay, we need the inverse map. Okay, so the inverse map here is what? Is given by the map calculated by Kyron just now. Okay, so this is our inverse map. Huh? Yeah. Okay, yeah. So this is the inverse map. So we need to check where does our pi 0, 0 and pi minus pi send to. What's going on? Something wrong? Inverse of it. Oh yeah, correct. You are correct. Yeah, you are correct. But how do we define this map here? Wait, let me see. Am I doing something stupid? See. So
Let me see. Okay. Let me see that. Doing something weird here. Okay, so what am I trying to do? Okay, so here are the XY plane. Okay, here is the XY plane. Let's back out a bit. So here is XY plane, here is UV plane. Okay, so how you determine XY going to UV? Okay, how do you find UV from XY? Given XY, how to find UV? So this is actually given by the first part here. So this is just x minus y and x plus y. Okay, so what's this map here? So what's this map here? This is the inverse map, right? U equals to x minus y and x plus y. Okay, so this is the inverse map. Okay or not? Can follow? Can follow or not? I see confused. Oh. Oh, question? So first, okay, so I repeat again. So first we start out with an XY plane. Okay, we start with an XY plane. But now we turn it into a UV plane. Okay, UV plane. So meaning, give you an XY point, you need to give me a UV point. Okay, so how to get UV from XY? This is the first transformation I define here. Okay, is that right? Okay, so this is the way I get the UV coordinate. But okay, but how we phrase it? Okay, we phrase it like this. This is following the theorem definition. Okay, theorems says that we need to know where does the t sends to get the Jacobian. Okay, so t sends the new variable to xy. Okay, but we need to figure out when we want to figure out the domain in new variable, we need to take t inverse. Make sense or not? Yeah. Okay. Okay. So let's see what happened to this point. Okay. So these are XY point. So what are the UV point here? Okay. So UV point become what? So pi minus pi becomes 0. Pi plus pi is 2 pi. Okay. And then 0, 0 becomes 0, 0 again. And then pi minus pi becomes what? Pi minus minus pi become 2 pi. And then pi minus pi become 0. Okay, so you got these 3 points here. So let's see what happened. So 0 gets sent to 0. Okay. Pi gets sent to 0, 2 pi. And then pi minus pi gets sent to 2 pi 0. Okay, so next we need to figure out what are these lines. What happened to this line? Right? What happened to this line? Yeah, so we have to figure out what happened to this line. Okay. Let's call some name to this line. So let's call it R1, R2, and R3. Okay, let's call it this name. Okay. So what happened to R1? Okay, what is R1? R1 here is going from 0, 0 to pi pi. Okay, what is this line? This is actually the line y equals to x. Okay, this is the line y equals to x. You can compute the gradient, okay, which is pi minus 0 over pi minus 0, which is 1. Okay, so this is y equal to x line. Okay, and then this line is going from 0 to pi. Okay. Okay, so in this case here, what happened to my u and v? What happened to my u and v? Okay, my u and v here is equal to x minus y and x plus y. Okay, so because y equal to x, right? So on the first coordinate, I get 0. Second coordinate, I get 2y or 2x. Okay, 2y or 2x, doesn't matter. Okay. So what's this line here? U is 0 and then v is 2x. What's this line here? What's this thing? What's this thing? Your pi, your x is going from 0 to pi. So what kind of point you get? 0, 0, 0, 2 pi as your endpoint. So what's this thing? What's this? What is this? Is the y-axis. Y-axis from 0 to pi. Okay. So this is actually this line here, R1. Okay, is the y-axis. And let's check R2. Where is R2? Okay, R2 is easier. This is a vertical line. Okay, where is this vertical line at? This vertical line is at x equals to pi. Okay, R2 is the vertical line, x equals to pi. Okay, and then where's your y? Your y is bounded between by minus pi and pi. Yeah, correct. Okay, minus pi and pi. Okay, so what happened to your UV here? Okay, so your UV is x minus y, x plus y. So your x in this case is all pi. Pi minus y, pi plus y. What's this? What's this point here? I think this one, is it a bit hard to imagine for this? Is it harder to imagine? Is it harder to imagine this? How to imagine this? A minus y, pi plus y. Okay, you take off the same amount that you add to y. Is this hard to imagine or not? Okay, how about try something else? Maybe change variable. How about we change a variable? Change to w. So let's w equals to pi minus y. Then y will equal to pi minus w. Okay. So in this case here we have w and pi minus w. Okay. Is this easier to understand or not? Easier to understand? So in this case here, what do we have? We have we get 0 to 2 pi. We get this. I think we get this. Stop here. Is this easier to think about? No? Not easier. Not easy. Let me think how. I think it's closer. It's closer. Okay. Let me show you one other thing. What is w minus w? You know this line here? W minus w. Huh? Y equals to minus x. Okay. But now I shifted all my y my second coordinate by pi. So I shift this line out by pi. Yeah. So this is what is this line here? This is a y equals to pi minus x line.
Yeah. 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 Pi minus x line. Yeah. Okay. So what happened to this line here? So this is this R2 here. This is the R2 here. Okay, R2 get mapped to this line. So y equals to minus x shifted up by pi. Actually shifted up by 2 pi in this case here. Is it? Yeah. Need to check this. I think there's something wrong with this. Maybe you need to check this. Check this. Okay. Check the domain change. I think everyone lost already. Lost already. Yeah, I mean, yeah, I mean, yeah, I mean, I mean, I don't know how to say. You ask question, yeah. Yeah. Question. I mean, you have to keep yourself going, right? So I mean, Chimpo, right, Chimpo? You don't know why what? I want to do this. I don't know why I want to do this. You don't know why I want to do this. Oh, I mean, in the exam, right? This picture here is not given. Yeah, so if this picture is not given, then you need to figure out what happened to this shape. Okay. Yeah. So you need to figure out what happened to this triangle. Okay. So that's mean yeah. So you need to check what happened to all these boundary, and then check what happened to the point inside. Okay. I mean, there's something to check here or something to see here. Okay. Yeah. And then are you convinced you need to do this? Yeah. What? I mean, how to say? Yeah, question. It's too high. It's too high. Okay. Oh, because I leave out the pi plus y, is it? Because I leave out pi plus y, is it? Yeah. Okay, I think you are right. So it's a pi plus okay, right. Yeah, you're right. So pi plus this whole thing plus y. So this is actually w of 2 pi minus w. Okay. Is this a domain change, right, or not? This interval? I think we can check, but yeah. Okay. How about now? How about the rest? Don't rely on me. So you need to put in some effort. I can give you some guidance. Yeah. I mean, are you happy with this R2 sending to this R2 here? Are you happy with this? Happy with this? Yeah. Happy or not also cannot answer. So how? Happy or not? Some of you happy. How about the rest? Okay.
Sling. Do you get it? You don't know? Don't know mean no. Don't know mean no. Huh? Don't know mean no. Okay, so how okay, okay, so first of all, do you all know what are we going to do? What are we trying to do here? We are trying to use some transformation and then change this integral to something that's easier to compute. Right? Okay. Why is this hard to compute? This is differentiating with respect to dx dy. Okay. Both of these contain x and y inside your function. Right. So what you have to do? By part, right? By part. Not by part, substitution. Substitution work or not? Expand. Oh, expand. Oh, okay. Expand use the double angle, is it? Use the double angle and then I think you still have mixed term or not? You still have mixed term? I know, but when you take the sum of the product have mixed term or not? You get what I mean? So you will have cosine, sine, something like that together, right? So you have product of variable. So I think it's hard. Okay. So what to do here? So we just change. Yeah, we just change the variable inside our cos and sine function into a single variable. Okay. But at the cost of introducing this transformation, we need to introduce the Jacobian. Okay. We need to introduce the Jacobian. Okay. How about let's do the Jacobian first? Okay, let's do the Jacobian. What's the Jacobian in this case? Okay, so we have this map here. So let's do what's the Jacobian is. Copy and then paste. Okay, so what's the Jacobian of this map here? Remember what we said about Jacobian? We need to take all the possible partial derivative. Okay, so for the core domain, we arrange as a row. Okay, we arrange as a row. And then for the domain, we arrange as a column. Okay. So in this case here, what are these four entries? What are these four entries? Ying. What are these four entries here? 1 over 2. And then what else? 1 over 2. And then only 1 over 2. And then 1 over 2. Okay, good. So in this case here, we got what? 1 over 2 times 1 over 2, 1 over 2 minus 1 over 2 times negative 1 over 2. So altogether you get 1 over 2. Okay, altogether you get 1 over 2. So in the end, what happened to our integral here? So let's write down the integral. So it's just a double integral r, and then cos x minus y sine x plus y. Okay, and then dA. So this become what? Under the change, you become cos of u times sine of v. Okay, multiplied by the Jacobian, we got half, and then du dv. Okay, next you need to figure out what's the integration domain. Okay, you need to figure out what's the integration domain in this case here. Okay, so how to figure out the integration domain? We need to see how this map get, how this triangle get mapped to UV plane. Okay, UV variable. So that's why we did all the stuff we do just now. Okay, but we haven't finished yet. We haven't quite see where R3 goes. Okay, so what is R3? Okay, R3 is actually opposite of, is a mirror reflection of R1. okay, which is y equals to minus x. Okay, y equals to minus x. So let's do it. Let's do it. So R3 is the line y equals to minus x. Okay, and then going from 0 to pi. So in this case here, what happened to our UV? Okay, so our UV is x minus y, x plus y. So in this case here, x minus y become 2x. Okay, x plus y becomes 0. Okay, so this is the 2x and 0. So the y coordinate is always 0. Okay, so this is a line. This is a line y equals 0 from 0 to pi. Okay, which is exactly this horizontal line here. Okay. Here's the direction. So here is the direction. So this is R2. Okay. You know how I get this direction or not? You know how I get this direction? You know how I get the direction? We only know, right? So how do I get the direction? Because we know how all the vertex get sent to. Okay, so we can exactly place. Let me see. Am I doing something wrong again? Let me check. So, okay. So let's see. So you see, pi, okay, pi gets sent to where? Pi gets sent to 0 to pi. Okay, pi gets sent to 0 to pi. Yeah, 0 to pi. Where's 0 to pi? Actually, I draw something wrong here. So 0 to pi is this point here. Okay. And then where is 0, 0? 0, 0 gets sent to 0, 0 again. Okay. And then pi and minus pi gets sent to pi 0. Okay, 2 pi 0 is here. Okay. Let's say we give an orientation for the first triangle here. And then you can see that based on how this line get mapped to and how this vertex get mapped to, we can determine we can get the same orientation from before. Okay. So for example, what? For example, here is R1. So this point gets sent to here. This point gets sent to here. So meaning we got the direction. Oh, okay. Makes sense or not? Okay. And then how about R2? Okay. So R2 is going from pi to pi minus pi. Okay. So pi is here. And then pi minus pi is on the other side. So this is the one. Okay. How about R3? Okay. R3, if I put from 0, 0 to pi minus pi, then following this line here, 0, 0 is here. And then pi minus pi gets sent to 2 pi 0. So this is the right configuration. Okay. Yeah. Okay. Yeah. Any question or not? Okay, so the next step is to write out this domain. How to write this domain? How to write this domain here? To write this domain. What time is it? Okay. Well,
Okay, after we done this, then we will finish. So what's the domain? What's the domain here? Okay, so I mean we need to fix which order we want to take first, right? Okay, which order do we want to take? du dv or dv du? Let's fix one, du dv. Okay, let's fix one, du dv. Okay, so in the v direction, we are integrating from where to where? 0 to 2 pi. Okay, good. So 0 to 2 pi. How about the u direction? Okay, let's write down first 0 to 2 pi. So what happened to u? Okay, when I fix a v, what happened to my u? Okay, my u is controlled by two lines. What are the two lines that bound my u? Is bounded below by u equals to 0 and bounded above by this line. What's this line? What's this line here? How to describe this line? Equals to 2 pi minus, v equals to 2 pi minus u. Okay, correct? Just now it says that this is the minus x line and then shifted up by 2 pi. Okay, so this is our integration domain. So let's put it down. Integration from 0 to 2 pi minus v, and then half cos u sine v du dv. Okay, so good. So what's the next step? What's the next step here? So how to integrate with respect to u? Cos u. So what do you get? You get sine u, sine u, correct? Sine u plus sine v integrate from 0 to 2 pi minus v dv. Okay, and then altogether I get sine v times minus sine v. Is that right? I think I skipped something. Okay, so maybe let's substitute it in. So this is 2 pi. This is a 2 pi minus v times sine v, and then sine 0 is just 0. Okay, so what is sine 2 pi minus v? Sine 2 pi minus v. Negative sine v. Okay, good. Okay, so you get this integral here. Okay, so this integral here, is it straightforward or not? So what's this? So this is just cos 2v minus 1 over 2. Is that right? The double angle formula. Okay. Okay. And then continue. So just integrate this. You get 1 over 4 of sine 2v over 2 minus v from 0 to 2 pi. Okay. Which is equal to negative pi over 2. Yeah. Any question? Any question before a break? So I mean, yeah, so the key point here is
you do the transformation. Okay, you do the transformation. You need to find the Jacobian. Okay. After you find the Jacobian, you need to know how your domain get changed. Okay. Yeah, how your domain get changed. Very important. Okay, because this is a linear change. Okay, so this is a linear change. So what's a linear change in R2? It's just some translation or shear or rotation. Okay, because these are the linear transformation in R2. Okay, if it is not linear, then you need to be careful. Okay, you need to be careful. You can't just check what happened to the boundary. Maybe it get flipped. Okay, inside out is possible. Okay, but since this is linear, so everything inside will stay inside. Yeah. I think I'm right. Things could get complicated, but if it is linear, I think it's still easy. But it's non-linear, then it is hard. Yeah. Linear stuff is easy because you can write down the matrix. Yeah, linear. So that's why you learn linear algebra. You didn't learn non-linear algebra, right? Yeah. So you learn linear algebra. So linear algebra, you can deal with matrices. Okay. Okay. So the thing you need to absorb to that is change of variable. Okay, and then Jacobian. How to find the Jacobian. And then how to change the domain. Very important. Okay. And then next class we will go into vector function and then vector calculus. Okay. Linear algebra plus calculus. Yeah, together. Linear algebra plus calculus. Is that the point? I thought we already passed through that. We already go through that, right? We already gone through that second derivative test and then maximum minimum value. Yeah, we go through that. Yeah. Why do you guys have that? Hessian, is it called Hessian? Oh, only one page. Application is it?